This is Stephen Balbus. I'm an astrophysicist at the college, the civilian professor of astronomy. I would like to read from a book written by a great physicist, Kip Thorne, called Black Holes and Time Warps: Einstein's Outrageous Legacy. It came out in 1994. It is a wonderful book, one of the best popular science books that I've read, and it discusses the history and the details of Einstein's theory of gravity in the form of general relativity. It is admirably clear. The book also speculates on what developments the upcoming 21st century will bring. The speculations on the future of the detection of waves of gravity, at the time still just a hope, were brilliantly fulfilled about 4 years ago with the detection of such radiation from a pair of colliding black holes. Many such sources have since been detected, and the field of gravitational radiation is rich and exciting. Other optimistic speculations at the time, for example, on the quest to unite the laws of gravity with those of quantum mechanics, still remain a task for the future and an object of current speculation. My reading is from the concluding paragraphs of this marvelous book. What can we expect in the coming century, the second century of Einstein's legacy? It seems likely that the revolution in our understanding of space, time, and objects built from space-time warpage will be no less than in the first century. The seeds for revolution have been laid. Gravitational wave detectors will soon bring us observational maps of black holes and the symphonic sounds of black holes colliding, symphonies filled with rich, new information about how warped space-time behaves when wildly vibrating. Supercomputer simulations will attempt to replicate the symphonies and tell us what they mean, and black holes thereby will become objects of detailed experimental scrutiny. What will that scrutiny teach us? There will be surprises. Ultimately, in the coming century, most likely sooner rather than later, some insightful physicist will discover and unveil the laws of quantum gravity in all their intimate detail. With those quantum gravity laws in hand, we may figure out precisely how our universe's space-time came into being, how it emerged from the quantum foam and froth of the Big Bang singularity. We may learn for sure the meaning or the meaninglessness of the oft-asked question, what preceded the Big Bang? We may learn for sure whether quantum foam produces multiple universes with ease, and the full details of how space-time gets destroyed in the singularity at the core of a black hole or in the Big Crunch, and how and whether and where space-time gets recreated again. And we may learn whether the laws of quantum gravity permit or forbid time machines. Must time machines always self-destruct at the moment they are activated? The laws of quantum gravity are not the final set of physical laws along the route that has led from Newton to special relativity to general relativity and quantum theory, and then to quantum gravity. For the quantum gravity laws will still have to be unified with the laws that govern nature's other fundamental forces, the electromagnetic force, the weak force, and the strong force. We will probably learn the details of that unification in the coming century, and again, most likely sooner rather than later. And that unification may radically alter our view of the universe. And what then? No human today can foresee beyond that point. And yet, that point may well come in my own lifetime and in yours. Thank you very much for listening.